Okay, so last time we were looking at how to encrypt long messages which are not of the length exactly n, and we took them to be multiples of n, and we were looking at stream ciphers which allowed us to encrypt the entire thing, right? So recall our encryption last time looks like recall encryption system looks like the encryption scheme looks like um, encryption k of m is equal to r comma fk of r XOR sum with m, and that is my ciphertext. It has two parts, right? Where k was a uniform key and r was generated uniformly. F was my what was it called? Keyed length preserving pseudorandom function, right? And we saw that if R repeats, the security fails. If R repeats, security fails. And we said that, oh, it can happen to, it can happen with negligible probability, and so we are actually fine, right? So it's it fails in actually the exact same way, uh, exactly analogous to the failure of one-time pad to the multiple encryptions using one-time pad scheme. Right? One-time pad fails for um, multiple message encryption using the same key for exactly the same reason that here it would fail, right? And so there are two ways of making an attack on a scheme that could break it. So let F be a block cipher. Be a block cipher. Okay. So in that case, we can attack our CPA scheme by two ways. Two general ways, two general CPA attacks on a scheme. And the first one is if F is not used correctly. So F not used correctly. Okay. What does that mean? Some part of the plain text is actually visible, or F is not used with a random unknown key, right? Some key is repeated or something. For example, uh, some function of plain text, function slash part of plain text directly leaked in ciphertext, or Another example is if we don't use a random key. If it's not used with a random key. So for example, encryption KFM is equal to R comma FRM. Okay. An attacker knows what kind of scheme you have, and if you have the scheme, they're obviously going to go, oh, the first k digits are my key. First some digits are my key. I'm going to use that on my function, right? So this would be a horrible scheme that could fail even if I'm using a good F, right? And another way it can be failed is if you get it to evaluate on the same input twice in the exact same way. Cause F to be evaluated on the same input twice, right? So for example, any deterministic system scheme would fail for this. Deterministic scheme, including the one-time fad, fails when you do this, right? Or if you take something like encryption K of M1, M2 is equal to R FK, FK R of M1, and then if you mistakenly did FKR of M2, rather than changing this to some other, maybe M1 or some other scheme, right? So in both of these cases, you can fail your secrecy, okay? The other thing we saw were stream ciphers. Stream ciphers, which we saw some examples of using the control cipher or the CVC method, right? However, the way we defined them, they were always using blocks of length n, right? They were still outputting like f fixed length. So as we defined them, PRGs are limited. Right? They have fixed length output and they produce output in one shot. They have fixed length output and they produce output in one shot. They produce output in one shot. And so our encryptions were slightly restricted in that we could only encrypt by n and use those. However, with stream ciphers where we saw, oh, the CVC method and CTR method, we could encrypt long messages. We'll learn how to pad messages maybe at the end of this one or maybe tomorrow. And that will allow us to encrypt messages of any length, right? Even yesterday when we did, technically we only encrypted messages of length multiples of n, right? There were blocks of length one or two, sorry, ln, each block was of length um, n or something, and we encrypted those. But in practice, we can do it for any length. In practice, PRGs are based on stream ciphers, are based on stream ciphers. Okay, so in real life, things are slightly better than the CBC and CTR method and these things. You don't need to make blocks and encrypt with that. You can do it, but there are other methods also. You can get a stream cipher which outputs completely long bits by itself. Okay, so this works as can be viewed as producing an infinite stream of pseudorandom bits on demand. Okay, and because of that, it's much more flexible and more efficient. More flexible, more efficient. Technically, in that case, you don't have to pad your messages to the exact length, because you can always more or less be like, okay, I want it for some random length that I want. I'm going to take these many bits, get my stream cipher to output those many bits. They're going to be pseudo-random, and use that. Okay? And so how are these constructed? So they're constructed by a pair of efficient, which is polynomial time, this thing, but they are deterministic algorithms. Pair of efficient deterministic algorithms. Okay, which are generally referred to as init and get bits. Initialization, init, and get bits. Okay, and init takes a seed S naught, takes a seed, S, and an optional initialization vector, and optional initialization vector, and outputs a state S naught, which is the initial state, and outputs initial state st naught. Okay, what does get bits do? Oops. Get bits takes the current state, st, right? Which, if you're in the initial, it's st0, but it might be stn, whatever state it is, and outputs a bit y along with updated state st prime. st prime. Okay, so that the state has now changed. Okay, now yes, the ideally you want it to output a bit at a time, but that's really slow in a way. And so in practice, you would generally want a block rather than a bit. So in practice, why would be a block? Would rather than a bit. Okay. So stream ciphers then allow you to get as many bits from the initial seed as you want. So can use int get bits to generate any desired number of output bits from an initial seed. And so in terms of diagram, I'm feeding my initial seed and initialization vector, if I want the second one, to init, which outputs a state st0, right? This gets fed to get bits, which outputs y1, state becomes st1, get bits, gives me another bit y2, st2, so on, right? Till I get as many bits as I want. Okay. So informally, a stream cipher is secure. Stream cipher is secure if the output stream generated from a uniform seed, if output stream generated from a uniform seed, is pseudo-random. Okay, what does that mean? I.e., regardless of how long the stream is, you should not be able to distinguish whether it's i.e. regardless of how long the output stream is, as long as it's polynomial, because if it's more than polynomial length, of course, any efficient distinguisher will not be able to distinguish it. It won't have time to read all of it, so long as it's polynomial. Right? The book has a formal definition, but we are not going to really go into that. Okay. Here's just some extra information about stream ciphers. I'm not going to go into super much detail about it because we don't really need it, but just some information so that you had. So there are a couple of modes of operation of stream ciphers. Modes of operation. Which is synchronized and asynchronized. Synchronized and second unsynchronized. So what is the synchronized mode? Synchronized. This is the easier to understand and for us perceived mode. So the sender and receiver always maintain the same state and must be synchronized. Sender and receiver maintain state, which is called they are stateful. Stateful and must be synchronized. So what does that mean? If the sender has state SD7, the receiver's stream cipher also must have state SD7. Okay, so which makes sense in the context of limited message where you're sending messages in the particular order and no messages being lost. So a limited time communication method, communication session actually, where messages are received in order and are not lost. Okay, if the messages were lost, that would be a very big problem because now you might try to encrypt a message which was encrypted with state 6 to while by using your encryption state, which is only at stage 4 maybe, since 2 messages were lost, right? So in terms of a picture, it looks like sender, receiver. I'm spelling receive correctly? Receive, yeah. So U1, so both of them have the same, what do you call? What's it called again? What should I call this? Seed, right? Both of them have the same seed, right? And they feed it to init. If they're using initialization vector, that will also have to be the same, okay, to get the state st0. Okay, both of them have that gets fed to get bits, goes to state st1, you get some y1, you're using that to encrypt the message m1, which is now a ciphertext C. 1 if I'm encrypting M1. Well, if the receiver also has the same exact setup, get bits st1, then they are also going to have the exact same y coming from their stream cipher, right? And they are going to get then, by XORing with C1, the message M1 that was sent, right? Easy peasy, easy to understand, okay? Now the unsynchronized mode is slightly harder to visualize in terms of how it works. Unsynchronized mode. So now suppose these messages were being sent at some point of time, they're being received at some other point of time, maybe some message was lost and later found, whatever. Now you no longer have that the same state is going to be maintained, right? And so how do you still make things go work? So you choose a random IV, random IV to encrypt next message. To encrypt next message. Okay. And the idea is going to be, it's going to be similar to the CPA secure systems we first saw, right? But we are going to handle arbitrarily length messages better than ciphertext expansion. Okay, so similar to the first CPA secure scheme, secure scheme we saw. But natively handles arbitrary length messages. Length messages with better ciphertext expansion. Okay. So how does this work? The idea now is that the initialization vector, which is your key, is being shared. So again, keys need to be shared, right? Your S is given. So both of them have the same S. Sender, receiver. Okay. S. IV. IV. S. Init. Okay, so there's a list of maybe S that you're initialization vectors that you're going to use, and or you have some way of telling that, okay, this is the one that I'm going to use this time. Get bits. Okay. Now, it doesn't matter what your state is. It's always going to be state 0 technically. Okay. But it's the initialization vector that's, once it's hit, it's going to keep producing as many what do you call bits as I want, till I stop. Right? I have to share the IV. Okay, but it doesn't matter if the states differ at some point, because technically there is no state. There is exactly one state, st0. Okay, so note. Note. So this is very similar to the CPA secure scheme we saw before, and hence we need it to be um, pseudo-random function. Note that for security. The stream to be a pseudo-random function. Okay, which means, i.e., for a fixed seed, for a fixed seed S, the output stream cipher when using different IVs should all look uniform and independent. Okay, so if I'm using different IVs, it should look as if I am sending out uniform things. Otherwise, I will be able to find a distinguisher uh, which distinguishes my Y's, which is the encryption text. And if Y is being distinguished, that technically allows me to distinguish between my M's, between my M's if I'm finding C, if I have looked at C. Okay. Okay. So we are not going to go into super much detail about uniform and not uniform. What do you call synchronized and asynchronized states? However, everything we have seen so far is only if my attacker is passively listening to things and maybe has some idea of how the messages are encrypted. So even if they're doing chosen plain text attacks, they're not interfering in between. So so far we have been assuming attacker is passive eavesdropping. Passive eavesdropper. Okay. Even if they carry out a chosen plain text attack. They're not actively interfering in my communication. They're basically looking at some messages that are being sent and trying to decode from there, right? Now, what if the attacker can be active? Question: what if the attacker can be active? What does that mean? I.e., they can actively interfere with the communication channel. Interfering with the communications channel. Okay. In that case, are our systems secure, or is there something that needs to be taken care of more? Right? So, for example, U1 sends a message to U2, which is with a key K, C encryption K of M, right? And they send a C. But now there is something that's happening and they're receiving C prime. M prime decryption K C prime. Okay. If there's an active interference, can my communication system still hold true? Like, can I get my messages to be secure even if I do such a thing as change the message slightly? Would the attacker be able to tell, okay, this is how the system is working, so these messages should get encrypted with this? Okay. So for that, we are going to create a new definition: malleability. Malleability. Okay. What is malleability? Informally, again, the definition is in the book, but I'm going to, for now, go with the informal definition. A scheme is malleable is malleable if it is possible to modify a ciphertext and predictably change and cause a predictable change to the plaintext, and thereby cause a predictable change to the plaintext. Okay. And the thing is, we don't want our things to be malleable. Malleability can be dangerous. Okay. So for example, if encrypted bank transactions. Suppose I can change something and send a message. That is going to cause a lot of trouble, right? Suppose while I don't know the exact message that is being sent, if I know, okay, this is what the message looks like, maybe I can change the ciphertext and change the transaction happening, right? I don't want such a thing happening. So it is better if my system is not malleable. But the problem is every scheme we have seen so far is malleable. All the schemes we have seen so far are malleable. For example, if you take the one-time pad, okay, even if I say it's perfectly secure, so we are not in the pseudo one-time pad, even if you take the perfectly secure one, right? Encrypt two messages. Encrypt messages. M0 is equal to 0 to the power n, and M1 is equal to 1 to the power n. Okay. Well, get ciphertext C. Get ciphertext C. Okay. Okay, if I'm doing it by the newer pseudo random thing, so that it's multiple message secure and secure under what do you call CPA secure. It's going to look like CPA, and the CPA secure version is going to look like some ciphertext R comma S. Then what do? Change first bit of X. Change first bit of S. Okay. Uh, Now we can check. Now it becomes unsecure whether now either this is going to give either the decryption is 1 then 0 to the n minus 1, or 0 times 1 to the n minus 1. So I have changed by changing the ciphertext slightly. I know what change I have done. Like, I can predict what the change is. I might not know if it is 1 0 to the n minus 1 or 0 1 to the n minus 1. And with the next type of attack, if it's an active attacker, if I can figure out what the encryption decryption of these two is, I can tell which one it was, right? So mm, what kind of attack are we doing here? Um, we are now going to look at what is called the chosen ciphertext attack. So, chosen ciphertext attack. Okay. So, what is the chosen ciphertext attack? Um, the idea is I can change the ciphertext and then observe what is the decryption. Okay? Model setting where the attacker can influence what gets decrypted and observe the effects. Okay. The question then becomes, how do you model such a thing properly? How to model. Okay. And the question is, what do you mean by influence what gets decrypted? If I give them M1, M2, get an output C, and they can decrypt C, then of course they can tell whether M1 was or M2 was encrypted, or M0 or M1, right? That sounds dumb. But we want that. We want almost that. So allow attacker to submit ciphertext ciphertexts of their choice. Let me put a star here. Okay, to the receiver. Receiver, and learn the corresponding plaintext. Okay. However, this has to be strictly better than my CPA. So I'm going to say this should be in addition to being to the CPA attack. In addition to being able to carry out a chosen plaintext attack. Okay. What is the one thing that's star? With one exception. The exception. 0 or 1. Sorry, let me just say C, which is encryption of MB. Okay, that's the one that we are not going to allow it to be able to break. Okay, everything else is fair game. So how do you model this? CCA security. Define a randomized experiment. Private key encryption CCA a comma pi of n as follows. Okay. First step, you feed the key generator 1 to the n. So basically you're telling it what n is. It outputs a key of length n. Uniform random key. You give it to the attacker A. Tell it what n is. It interacts with this, and with the encryption oracle, interacts with encryption oracle ENCK dot. However, it's no longer just the encryption oracle and the decryption oracle and a decryption Oracle DC dot, and then outputs M0, comma M1 of the same length. Okay. Step 3, choose a uniform B, encrypt one of the messages using your encryption oracle, MB, and give C to A. Give C to A. Stage 4, all this while, and even after the message, A can continue to interact with both ENCK and BCK. He can continue to interact with ENZK and BCK, but it cannot request decryption of C. Cannot request decryption of C. Okay, that is the one thing they're not allowed to decrypt. Step 5, A outputs B prime. A outputs B prime. A succeeds if B is equal to B prime, and experiment evaluates to 1, and experiment evaluates to 1, otherwise 0. Okay, that's the randomized experiment, and we will call something CCA secure if the standard thing holds, which is pi is CCA secure. If all probabilistic polynomial time attackers A, if for all probabilistic polynomial time attackers A, there is a negligible function epsilon such that the probability of the experiment succeeding when is still 1/2 plus epsilon n. Okay? And now, malleability implies that it is not CCA secure. If a scheme is malleable, then it is not CCA secure. Example, continuing from before, change first bit of S and call it C prime is equal to r comma s prime. Okay, then c is not equal to c prime, so we can ask for decryption. So we can ask decryption k of c prime. Output 1, output b prime is equal to 1 if decryption c prime is equal to 1, 0 to the n minus 1. Output 0, b prime is equal to 0. Otherwise, okay, technically, because of the way I'm doing, I know this has to be the case that decryption k of c to the c prime is 0, 1 to the n minus 1. Oh, yeah, I flipped them by accident. B prime is equal to 0, B prime is equal to 1. Okay? And in that case, I'm always going to succeed. Okay? If I give my messages M0 and M1 in that form, I'm always going to succeed with probability 1. Similarly for similar tag works for every malleable scheme. Okay? Therefore, CCA security implies non-malleability. Non-malleability. Okay? Now the question is this realistic? Is this too strong? The answer is maybe? Question is this realistic or too strong? And the answer is there are real world scenarios where you can reasonably see what is happening if you send encrypted messages. For example, there are real world scenarios where this might occur. Okay. For example, when we saw the Midway Island exercise, where the American Army managed to do chosen plain text attack and get information, they could have as well sent out false information, a false message that could be in certain frequency, and hope to see how the Japanese respond, right? And while they can't see what they have decoded the message as, what was the exact decoding, depending on the reaction, you can guess what the decoding was. Okay? And so while they might not be able to gain complete access to the decryption algorithm, there might still be a limited access to the decryption algorithm, right? And so maybe it's not available in full generality, but even partial generality is available in the real world, in which case it is something that you should consider. Another example is you don't want your bank getting messages, for example, encrypted messages that they can process and do financial transactions, right? So it is important that your security system should be CCA secure as well. Let's stop here for today.